Well, hello everyone, and welcome back. So, on these last two tabs, we're going to be looking at t-tests instead of z-tests. And the difference between t and z is that now we don't know the population standard deviation. In the z-test, we didn't know the population mean either, and we still don't know it here. So we're getting everything off the samples when it comes to t-tests. And that means t-tests are slightly less precise than z-tests. But we can still make strong conclusions. So the manufacturer of an MP3 player wanted to know whether a 10% reduction in price is enough to increase the sales of its product. To investigate, the owner randomly selected outlets to sell the MP3 players at reduced and regular prices. At the 0.05 significance level, can the manufacturer conclude that the price reduction resulted in an increase in sales? The population standard deviations are unknown and cannot be assumed to be equal. So that's why these tabs are called t-test with t-test unequal, because it's unequal variances. We'll actually see that. Okay, so the case is we're looking for an increase in sales. So again, we're one-tailed right. Distribution, and by the way, one of the reasons we do the prep with one-tailed right is because right is harder than left. So when you get to a left test, hopefully it'll be easier for you. So this is t. That's important. The null is no significant difference. And the alternative is that the reduced population mean is significantly greater than the regular population mean. So let's get the average. Of reduced and reduced standard deviation. So now we're calculating standard deviation of the sample. Remember, previously, we were just given the standard deviation of the population. And then the count. And for the regular, standard deviation. And this is the .est version because it's sample standard deviation, and then the count. All right, so let's look at what we're all about. So if the two samples came from the same population, from this blue band, then we would say we would fail to reject. But if they're different enough, in particular the dotted or the dashed line here is different enough, then we'll say it's from a different population. So here's where we're actually at. So what we're trying to decide is this gap so big that they wouldn't fit inside the blue band together or not? And in order to answer that question, we have to consider, well, what if the sample had been here? What if it had been here? And we have to look at all those different differences, all those different subtractions, and then get a distribution of those subtractions. And that's what's coming next. So the calculation here is very similar, except now we're substituting the sample standard deviation instead of the population standard deviation because we don't have it, which makes the test less precise, but again, still good enough that we can make strong conclusions. All right. And then our observed difference here is this minus this. And so here we've got our expected difference, or expected variability of 9.23. Our observed difference is less than that. So this is, in all likelihood, going to be a fail to reject. And you can kind of see that here. I mean, this is where we're at with the difference, which is right here in the sort of the the tall part of the curve. We're not out here in a tail. But let's go ahead and do it mathematically. So our t-score is the observed divided by the standard error, or expected variability. And the probability of that is, now here it's not norm.est, it's t.dist. Dot. Okay, and then there's different versions of the t-test. And hopefully there is a right version, t.dist.rt for right looking. So there's more options here, which is nice. But then we also have to throw in degrees of freedom, which is this number here. Now we're calculating this number for you, because if you double click on it, you can see it's a pretty big formula. But it's interesting, the formula takes into account the samples, standard deviations, and sample size. Okay. Alpha is 5%, and then this is, what's nice is we always do these the same way, so once you kind of get the hang of this, you should be good. Except, because it's a t-test, instead of norm, it's going to be t dot inverse of that number with the degrees of freedom, which was this number here, the 11. And unless I lock the 11, I won't be able to copy it across, so I'm going to lock the 11. And then remember, for this one, I do the 1 minus the probability. So this is the number we're going to work with because we are one-tailed right. And you can see it right here, t critical 1.80, 1.80. And we don't make it there. So that's why it's failed to reject. Then let's look at our confidence intervals. So we start out with the observed difference. And take that minus the standard error times this number. Remember, the reason we're picking this number, the 2.20, is because that's what an alpha 5% in a two-tailed test would be. But it also, remember, confidence intervals are also two tails, right? Because there's a lower and an upper. And that's why we pick the two-tail. That plus the standard error times that. All right, so there's our confidence interval, and our confidence interval is built off of our observed difference, but it includes well up inside of it the hypothesized difference, which is 0 if they come from the same population. So that's why this is a fail to reject. And I'll let you answer the questions over here in the answer block, and we'll see you in the next video.